Start. Okay.
Yes. Okay.
So, hello everyone. Welcome to the European Non-Associative Algebra Seminar. Today is August 28, 2023, and we have a talk by Elitza Hristova from the Institute of Mathematics and Informatics, Bulgarian Academy of Science. And she's going to talk on the GLN module structure of the nilpotent associative relatively free algebras. Please.
Okay, thank you very much. I first would like to thank the organizers for the invitation to give a talk on this very nice seminar. I'm very happy to be here. And then I would like to mention that my talk comes from the theory of algebras with polynomial identities, but I will define all the necessary notions from this theory, so no previous knowledge from PI algebras is needed. So let me start. Do you see my screen? I hope. We're going to, okay, thank you. We're going to work on a field of characteristic 0, k. We will denote it by k, at least in the first part of the talk. Then in the second part of the talk, we'll fix k to be c. But for the moment, any field of characteristic 0 works. And all vector spaces and all algebras will be over k. And we also require that the associative algebras have a unit in our talk. Okay, so now we fix V to be a finite dimensional vector space over our field K with a fixed basis x1 to xn. Then we have two objects that can be naturally identified once we have fixed the basis. This is the tensor algebra of the vector space V and the free associative algebra, which is generated by the set Xn. And we are going to use both notations. That is why we introduced them both. Okay, so then in our free associative algebra K of Xn, we define the usual double commutator by the usual formula. And then we extend this definition, defining commutators of length P using this recursive formula. And we do this for any p, for any integer p. So p in our talk will denote an integer, not a prime number, positive integer. Okay, so we define long commutators, and by IP we will denote the two-sided associative ideal in K of Xn, which is generated by all commutators of length p. These ideals IP, they are examples of the so-called notion of T-ideals, which is a very basic notion in the theory of algebras with polynomial identities. And a T-ideal in general is any ideal in K of Xn, which is closed under all K algebra endomorphisms of K of Xn, which means that if we take an element, a non-commutative polynomial from I, from our ideal I, and then we substitute all the variables with arbitrary elements from K of Xn, then we get again an element for the ideal I. So this is what a T-ideal is, and IP for any P is a T-ideal, which is not difficult to see. Now let us introduce also the notion of PI algebra. For this, it is convenient to consider also the free associative algebra over an countably infinite set, not only a set with n elements. So we take countably infinite set. We take K of X to be the free associative algebra generated by this set. And we say that an algebra A satisfies a polynomial identity if there exists a non-zero polynomial from K of X in any number of variables, here, for example, in m variables, such that when we substitute the variables with elements from the algebra A, then we get a 0 for every substitution. And if an algebra satisfies a polynomial identity, it is called a PI algebra. And basic examples that we all know are, for example, the commutative algebras, because any commutative algebra satisfies this polynomial identity, double commutator being equal to 0 for any two elements of the algebra. Also, finite dimensional algebras, they are PI algebras because it is not difficult to see that if A is of dimension R, then A satisfies the standard polynomial of degree R plus 1. Which is given. So these two are the first basic examples, and they somehow suggest that PI algebras are generalizations of both commutative and finite dimensional algebras. And we have one less trivial example, let's put it that way. If we take the exterior algebra, first of any vector space, then it's not difficult to see that the exterior algebra satisfies this polynomial identity, a triple commutator being equal to 0. This is for any vector space W. And if we furthermore require W to be countable dimensional, then basically, essentially, this is the only polynomial identity which is satisfied by the algebra. And being the only one, this is a result of Krakowski and Regive from 1973. I mean, when W is a finite dimensional vector space, then from the previous slide, we already know that A being finite dimensional satisfies also the standard polynomial. But when W is countable dimensional, A satisfies only this polynomial identity or everything that can be generated from it. Okay, and then we now want to see what is the relation between PI algebras and T ideals, and it is the following. The set of, it is straightforward. The set of all polynomial identities which are satisfied by a PI algebra A, they form a T ideal in K of X. And if we take only the polynomial identities in the first n variables, then we get a T ideal in the algebra K of Xn, which is generated by the set x1 to xn. And conversely, every T ideal can be represented as a T ideal of the identities satisfied by some PI algebra A. Right, so the two definitions of T ideal are equivalent. And one last definition before we move on with our talk. We call the class of all associative algebras which satisfy a certain set of polynomial identities Fi. The variety of algebras satisfying this set of polynomial identities. Okay, so these were the basic definitions that not all of them we will need. Now let us see what are the basic objects that we are interested in this talk. And this is the quotient algebra of the free associative algebra modulo the ideal generated by all commutators of length p plus 1. This is a PI algebra, and moreover, it is the relatively free algebra of rank n in the variety of all PI algebras that satisfy this polynomial identity. Why is it called the relatively free algebra? Because it is the free object in this variety of all algebras satisfying this identity. And more generally, when we take any T ideal I, then the quotient of K of Xn mod this T ideal I is the free object in the variety of all associative algebras that satisfy the polynomial identities from I. And we can think here as a starting example for the symmetric algebra S of V, because it is the free object in the variety of all commutative algebras. Okay, and now there is a natural action of the group GON on our vector space V because we have fixed the basis. And this action extends to the diagonal action on the free associative algebra K of Xn. And since any T ideal is a GON invariant, then the quotient algebra K of X mod I, K of Xn mod I, inherits the GON module structure of the free associative algebra. And a big question in the theory of PI algebras is to describe the GON module structure of K of Xn mod I for different classes of ideals I. And in our talk, we'll be interested in the class of ideals generated by long commutators. So we are interested, let me say it again, in describing the GLN module structure of this quotient. And here I just want to mention that this problem, finding the GLN module structure of such quotients, has an equivalent formulation in the terms of modules of the symmetric group. And many of the results that we will quote were originally written in this formulation. But in our talk, we'll translate everything in the language of GLN modules, which is equivalent. So now we know what question we're interested in. And let me now state what is known. For certain small values of p, there is a complete description of this GLN module structure. So let us see how it looks like. First, let us fix the notations. This is a brief recall on some GLN modules, which are probably known to everyone, but let me fix the notations. So by lambda, we'll denote a non-negative integer partition with n parts, which is just a non-increasing sequence of non-negative integers. And we recall that all irreducible polynomial GLN modules, they are indexed by such partitions lambda, and they appear as submodules of different powers of our original vector space V, different tensor powers. And the size of the partition is equal to the tensor power in which this submodule is in which this submodule appears. So the polynomial irreducible GLN submodules, they are indexed by partitions lambda and will denote by V lambda the irreducible GLN module which corresponds to the partition lambda. And we also recall that to each partition lambda, we can associate a Young diagram, which is just a diagram of boxes such that there are lambda 1 boxes in the first row, lambda 2 boxes in the second row, and so on, lambda n boxes in the last row. Okay, and now let us move on to describing the known results. First, we start with the well-known symmetric algebra, which, as we said, is the quotient of the free associative algebra modulo the ideal generated by all double commutators. So, as we all know, this is the sum of all symmetric powers of V, and each of these powers is itself an irreducible GLN module corresponding to the partition I000, or in terms of Young diagrams, the decomposition here has this form. We have Young diagrams consisting of only one row, which can be arbitrarily large, and the other rows, they have 0 boxes in them. Then also a classical result is when we take k of xn modulo the ideal generated by all triple commutators, then the decomposition has this form in terms of partitions, and in terms of Young diagrams, this is the sum of all hook-shaped Young diagrams, where the first row can grow arbitrarily large, and in the first column, we can, after the first row, we can have at most one box in each row. And there are 2 more cases that are known. This is when we take k of xn modulo the ideal generated by all commutators of length 4. Then in terms of Young diagrams, this is the decomposition. We write it in this concise form as a tensor product of some GLN module times the symmetric power of V. And then using branching rules, one can further decompose this tensor product into a sum of irreducibles. So in this case, we see that this decomposition is no longer multiplicity free as the previous ones, but it still is known. And k of xn mod I5 is also known, but already too complicated to be written down in one slide. But anyway, let us point out that it is known, and this is all in terms of complete decomposition. So as we can see, these are quite old results, which suggests that probably for higher values of P, this decomposition will be too complicated to be completely determined. But there are also some general results that are known, and let me also quote these results. So the first one is this classical theorem of a mitsuring and regive from 1982. It holds for any TIDO I, so let me state it in this form. So we take any TIDO of the free associative algebra K of xn, and let us write the decomposition of the quotient as a GLM module in this form. Then there exist integers k and l such that all non-zero multiplicities, their corresponding partitions are supported in hook diagrams of this form, which means that every partition lambda that corresponds to a non-zero multiplicity can be fit inside this diagram like this. So these are all partitions lambda that can appear in the decomposition. Or in other words, this means that we don't know much about the first k rows of our Young diagrams that appear with non-zero multiplicities, but from the k plus first row on, we know that the number of boxes in each row is bounded by the number L. Okay, and this theorem was improved by Barrow in 2005. So this is the theorem of Barrow. It says that all Young diagrams that appear with non-zero multiplicities in the decomposition, they are supported in diagrams of this form, where the integers, so there exist integers L, K, S1, and S2, such that this holds for all Young diagrams. And the number K is greater or equal to the number L. And this theorem can be also given a more precise form when we talk only about not arbitrary TIDOs, but TIDOs that are generated by long commutators. So let us see what is known here. We know that the number k is equal to 1 in this case, and the number L is equal to 1, which means that the first row of lambda can grow arbitrarily large, and the first column can grow arbitrarily up to n, and the rest of the entries in our partition is supported in this rectangle for certain values of S1 and S2. Okay, so this is a theorem, the theorem of Barrow, and what our contribution to this picture is that we give a value, exact value for this S2 here. So this is our first result, and let us see how this goes. So for this, we will need some more notations. So let us call commutators pure when their entries consist only of basis elements. And let us denote by Bn the subalgebra generated by all pure commutators. And the elements of Bn, they are called proper polynomials. And it is not difficult to see that Bn is a GLN submodule of K of xn. And furthermore, when we consider this natural projection from K of xn to the quotient K of xn mod IP plus 1, then we can regard the image of Bn inside the quotient, and we'll denote it by phi p of Bn. And this will be a GLN submodule of the relatively free algebra K of xn mod IP plus 1. And this is the subalgebra of proper polynomials inside K of xn mod IP plus 1. And here there is a very useful theorem of Drensky that says that as GLN modules, K of xn mod IP plus 1 is isomorphic to the tensor product of the subalgebra of proper polynomials times the symmetric algebra V. Which means that if we want to determine GLN module structure of this element, of this thing here, it is enough to determine the GLN module structure of the subalgebra of proper polynomials, and then use branching rules for the composition of tensor products in order to determine the GLN module structure of the object on the left. And this is what exactly we're going to do. We are first going to focus on the subalgebra of proper polynomials, and this is our result for this subalgebra. If we write its decomposition as a GLN module in this form, then our statement says that an irreducible GLN module V lambda appears with non-zero multiplicity in this decomposition. If it appears with non-zero multiplicity, then necessarily lambda 1 should be bounded by the number p minus 1. Or in other words, this subalgebra is finite dimensional because there are only finitely many partitions that satisfy this property. And there is one more remark here, is that this bound is exact, which means that for any p, for any such decomposition, we can find a partition that appears with non-zero multiplicity and for which lambda 1 is exactly equal to p minus 1. So we get an exact bound here on the partitions that appear in the decomposition. And let us give some ideas of the proof, since it is not very difficult. So first, it is not difficult to see that if we take the weight space decomposition of the subalgebra of proper polynomials, then the weights are indexed by n tuples of non-negative integers, and the weight space that corresponds to a weight mu consists of sums of products of pure commutators, such that the variable xi appears in each product exactly mu I times. And this means that if we want to estimate the largest value of lambda 1, it is enough to estimate the maximal number of appearances of the variable x1 in a product of pure commutators. And how can we do this? We just need to estimate how big products of pure commutators we can fit in our subalgebra. And then estimate, after we have estimated the length of these products, we can estimate how many times the variable x1 can appear. And in order to do that, we use some theorems about products of commutators. The first one is a classical theorem, which was first proven by Latyshev in 1965. And then it was independently rediscovered by Gupta and Levin in 1983. And this theorem, it holds for any integers m1 and m2, and says that if we take the ideal generated by commutators of length m1 and multiply it by the ideal generated by commutators of length m2, then this product sits inside this ideal here. And that theorem will already give us a bound on the number of appearances, the maximal number of appearances of the variable x1, and correspondingly a bound on the partition lambda, but this will not be an optimal bound. So we need some more theorems on such products of ideals in order to give an optimal bound. And so we use this better inclusion, which holds when m1 or m2 is an odd integer. Then the product of the two ideals sits inside this ideal. So we get a better inclusion. But since this theorem doesn't work if we drop the condition of one of them being odd, this is still not enough for an optimal bound. And so we add a small lemma here to make it enough for an optimal bound. And this small lemma says that if we take two commutators of even length, such that the last entry in the two commutators is the same arbitrary element from K of xn, then this product lies in the smaller ideal I m1 plus m2 minus 1. This statement is well known when we have double commutators. So for double commutators, having the same element, we know this is classical, that their product is then an element of I3, the commutator, the ideal generated by triple commutators. But it wasn't known, to my knowledge, about ideals of even length, not ideals commutators of even length, but greater than 2. And so we generalized this lemma to arbitrary commutators of even length. Okay, and based on these three statements, and of course their generalizations for arbitrary products of ideals, we were able to show the optimal bound on lambda 1. And now, once we have found a bound for the subalgebra of proper polynomials, we again use this tensor product decomposition, and we use branching rules. We use a special case of the Littlewood-Richardson branching rule, which is called the Pierre branching rule, in order to obtain the straightforward corollary from the previous result, which says that if we take K of xn mod the ideal generated by commutators of length p plus 1, then if a module V lambda appears with non-zero multiplicity M lambda in this decomposition, then a lambda 1 can grow arbitrarily large, but lambda 2 is bounded by the number p minus 1. And furthermore, as in the previous statement, this bound is exact, meaning that there is always a partition which appears with non-zero multiplicity, and lambda 2 is exactly equal to p minus 1. And let us see on the examples that this really holds. Just two examples. If we take again the known decompositions, so for example, the symmetric algebra of our vector space V, then in this case, P will be equal to 1. And according to our statement, lambda 2 should be less or equal to 0, or 0, since it cannot be negative. And this is exactly what happens. We have that the first row of our Young diagram can grow, but there are only zeros from the second row on. And similarly, when we take K of xn mod I3, then we have these hook-shaped diagrams. And our theorem says that lambda 2 should be bounded by the number 1. And this is exactly what happens. The first row can grow, but from the second row on, we can have at most one element. And of course, as we said, this doesn't hold only in these two cases, but the exactness holds for any value of p. Okay, now we can move to the second part of our talk. This is some applications of this result, which are applications related to the algebra of invariants of K of xn mod IP plus 1 for different subgroups of GLN. Let me say here that in classical invariant theory, one takes the symmetric algebra S of V, and then discusses the algebra of G-invariants for different classes of groups G. And for example, one big question is for what classes of G this algebra of invariants is finitely generated. So this was asked by Hilbert, and the Hilbert-Nagata, the famous Hilbert-Nagata theorem says that when G is a reductive group, then this algebra of invariants is finitely generated. Now, one way to do non-commutative invariant theory is to replace the symmetric algebra SV with the relatively free algebra K of xn mod certain ideal I and certain T ideal I, and then ask the same question: when is this algebra of invariants finitely generated? And in a series of papers, Domukos and Drensky have shown that if we take K of xn mod the ideal generated by long commutators, then the algebra of invariants, of G-invariants, is finitely generated for any reductive subgroup G of GLN and for any maximal unipotent subgroup G of a reductive subgroup of GLN. So in this situation, the classical results transfer also to the non-commutative case. In this case, this is like a generalization for the symmetric algebra V. And they have also shown that this is an if and only if statement. So if this ideal here was an arbitrary T ideal that doesn't contain a long commutator, then the algebra of invariants will not be finitely generated for every reductive subgroup. Okay, and what we want to do in our talk is that we want to find, since we know that this is finitely generated, we want to find a maximal degree bound for the maximal degree of a generator for these 5 subalgebras here, which are SON, ON, SON, SP in even dimension n, and this here is UTN. This is the subgroup of GON of all upper triangular matrices with ones on the diagonal. So the first 4 of these groups are reductive, and the last one is a maximal unipotent subgroup of GON. So for all 5 of them, we know that the respective algebra of invariants is finitely generated, and with using our methods, we want to find a bound for the maximal degree of a generator. And we'll denote this maximal degree by beta. And since we are going to use Hilbert series in order to find a bound for this maximal degree, here we have recalled the definition of Hilbert series, which works not only for algebras of invariants, but for any finitely generated graded algebra. And this is this form of our series. So it's a sum over I of the dimensions of all homogeneous components, AI times T to the power I. Okay, it is also a result of Domukos and Drensky that for these algebras of invariants, the Hilbert series is a rational function. And we are going to find for these 5 algebras a specific form for this rational function, which will help us find a maximal degree of a generator. In order to do that, we use these statements that tell us how to determine the Hilbert series when we know the decomposition of our initial algebra. So for any finitely generated graded algebra, and these theorems, they work over C. So from now on, we fix our base field to be C. And the first statement is due to these 5 people here. It says that if we take an algebra A, which is finitely generated and graded, such that each homogeneous component is a polynomial GLN module, and if we have the following decomposition of A as a GLN module, then for the Hilbert series of the algebra of G-invariants, we have this form where we have some restrictions on the second sum, on the sum of over all partitions based on G. And when the group G is SLN, then the second sum is over all partitions with equal entries, lambda 1 equal to lambda 2, and so on. And when G is the group of upper triangular matrices with ones on the diagonal, the sum is over all partitions lambda. There are no restrictions. So once we know the decomposition of A, we can find an expression for the Hilbert series of the algebra of invariants AG. And in joint work with Drensky, we have found similar statements for the other three groups of interest. So again, we take A to be finitely generated graded algebra, which is also a GLN module of this form. And when we know the decomposition is a GLN module, then the Hilbert series of the algebra of invariance has this form, where when the group G is the symplectic group, the second sum runs over all partitions lambda, such that lambda 1 is equal to lambda 2, lambda 3 is equal to lambda 4, and lambda 2s minus 1 is equal to lambda 2s. When a G is the group On, then the sum is over all even partitions lambda, and when G is the group SON, the sum is over all even or odd partitions lambda. Okay, and based on these results, now we are going to use them for A being our relatively free algebra K of Xn mod the ideal generated by long commutators. There, we don't know the exact decomposition, but we have found a bound on the values of lambda, and in this way, we can use this bound to find an expression for the Hilbert series up to some polynomial in the numerator. And this is the results that we obtain when G is one of the groups SLN or the symplectic group, SP2S. Then we have found that the Hilbert series is a polynomial. It's not a formal power series, but a polynomial. And the degree of this polynomial is bounded by this number, n times p minus 1. So in particular, this means that the corresponding algebra of invariance is not only finitely generated, but also finite dimensional. Okay, and as a straightforward corollary from finding this expression of the Hilbert series, we see that the maximal degree of a generator of this algebra of invariance is bounded by the number n times p minus 1. There is a similar statement when G is one of On or SON, but here the Hilbert series is not a polynomial, a rational function with a simple denominator, 1 minus t squared, and the numerator is some polynomial, which we don't know, but we can estimate the degree of this polynomial. And when the group G is the group of orthogonal matrices, then the degree of this polynomial is bounded by the number n times p minus 1 when p is odd, and n times p minus 2 when p is even. And when G is the group of SON, then the degree of this polynomial in the numerator is bounded by the number n times p minus 1. And there is one last, as a direct corollary from this statement, we obtain a bound on the degree of generators of the algebra of invariance. And here is the bound for the group On, and below is the bound for the group SON. Okay. And now a similar statement for the group of upper triangular matrices with ones on the diagonal. In this case, the Hilbert series of the algebra of invariance has this form. The denominator is 1 minus t, and the numerator is a certain polynomial, which we don't know, but again, we can estimate the degree of this polynomial to be less or equal to the number n times p minus 1. And as a straightforward corollary, we obtain a bound for the maximal degree of a generator of this algebra of invariance. Okay, and now we can ask the question, to what extent are these bounds exact or optimal? And we can check this when p is equal to 2, we can check the optimality of our bounds for p equal to 2, because when p is equal to 2, which means we consider c of xn modulo the ideal generated by triple commutators. In a joint work with Veselin Drensky, we have found explicit generating sets for these algebras of invariants for all the 5 groups that we have considered. And so we can check whether the bounds from our statements from before are obtained or not. So let us recall that the bounds in this case will be, so the maximal degree of a generator will be less or equal to n when G is one of the groups SLN, SP, SO, and UTN. And the bound will be less or equal to 2 when the group is ON. Okay, let us see how the generating sets look like. So when we consider the algebra of SLN invariants, then we have only one generator, and this is the standard polynomial of degree n. So in this case, we have a generator of degree n, and the bound that we have found in our previous statements is obtained. When we consider the algebra of SP invariants, then it is again generated by one element. It is this element. However, this element is of degree 2, and our previous statements say that the bound should be n. So in this case, the bound is not obtained. And as n grows, the bound is further and further away from being optimal. Okay. Let us see what happens in the other 3 cases. When we take the algebra of ON invariants, then this is a polynomial algebra. This is a free commutative algebra, which is generated by one element, this quadratic form. So in this case, we again have just one generator of a degree 2, and our bound here says that that we obtain the bound, because the bound is again 2 in the case of ON. For SON, we have two invariants of we have 2 generators of the algebra of invariants. This is the standard polynomial of degree n and the quadratic form. So in this case, we again have a generator of degree n. So the bound in this case is again obtained. And for the algebra of UTN invariants, we have that it is generated by x1 and by all standard polynomials of degree d, where d can grow from 2 to n. So we again have a generator of degree n, and again, the bound is obtained. So the conclusion is that when p is equal to 2, the bounds that we obtain on the maximal degree of a generator of the algebra of invariants are exact in all cases except when G is the symplectic group. And then we can ask the question of what happens when P is greater than 2. And our expectations are that the bounds will not be exact. And the reason for this is that our theorems, they give a bound on lambda 2. But we don't know what happens with lambda 3, lambda 4, and so on with the other elements of the partition. And they will play a role in obtaining these results here. So our expectations are that our bounds will not be optimal. There are some bounds, some numerical bounds. So far, nobody has obtained such numerical bounds, but they will not be optimal, and we will work on improving them. Finding restrictions not only about lambda 2, but also about the further lambdas, lambda 4, lambda 6, and so on. Okay, but this is still work in progress, and that's why I'm not going to talk about it. And there is only one last, there is something in the chat. What year is the Drensky theorem? Sorry, I see it right now. It's a node theorem. It should be from the 80s. I don't remember exactly. but 80 something. I mean, the theorem about the decomposition of k of x mod ip plus k of x mod I as a GLN module as a tensor product of the subalgebra of proper polynomials and as in the symmetric algebra. This theorem is somewhere from the 80s. I can check for sure. Yes, it's earlier than those papers. Yes, that's true. These are later papers. Okay. Sorry for seeing the question now. Okay, there is one more application that I would like to share. And it is related now not to the algebra of invariants of the relatively free algebra K of X mod IP plus 1, but to the algebra T of V, the tensor algebra itself. So we know the G-invariants for all these 5 groups. The G-invariants in the tensor algebra, they are known, but their descriptions are not, I mean, they are explicit in certain sense, but here we give some criteria when these invariants belong to the ideas generated by long commutators, which in our opinion, they are not straightforward from the description of the invariants themselves. So let me give here this criteria for the groups SLN, SP, and SO. And we have similar criteria also for ON and UTN, which I'm not going to give here. So let me first give the criteria for SLN and SP. So if we fix G to be one of these 2 groups, and if F is a homogeneous G-invariant in the tensor algebra V, which is of degree greater than n times p minus 1, then this element necessarily belongs to the ideal IP plus 1, the ideal generated by commutators of length p plus 1. And this is a straightforward reformulation of our theorems on the bounds of the maximal degree of generators that we had before. And there is a similar statement when G is SON. Let me say it here. So if we take a homogeneous G invariant in the tensor algebra, which is of degree greater than 2, then either this element belongs to the ideal I2, or F can be expressed by homogeneous invariants of smaller degree plus an element of I2. And if F is a homogeneous invariant of degree greater than n times p minus 1, then either F is an element of IP plus 1, or F can be expressed by homogeneous invariants of smaller degree plus an element, so up to an element of IP plus 1, F can be expressed by homogeneous invariants of a smaller degree. Okay, and that was all I wanted to say. So thank you very much for your attention.
Thank you very much for your talk.
Thank you.
Other questions?
Would you expect great difficulties when you try to replace the ground field of complex numbers by the real field? Because that would be natural from the perspective of nilpotent Lie groups.
With the real numbers, in the case of SL,
when you consider the free algebras and so on over them.
Right. I mean, in the first part of the talk, K can be the real numbers, but when we take algebras of invariants, one has to check. So for these theorems here, what we use is that we use the composition of GLN modules into irreducible, for example, SP modules. And these branching rules, they work over C, and I have to check to what extent they work over R. If they work over R, then the theorem is immediately holds immediately over R as well. The problem is whether when we decompose GLN modules as SP modules, what happens? So this is what has to be checked. If it works, then everything else is fine. And for SON, this holds. For SON, this holds. So yes, for SON, the theorem could be also over R. But for the others, has to be checked.
Thank you.
Thank you.
More questions? So let's thank Elitza once again.
Thank you.
Thank you for your talk.
And I thank you very much for your attention and for your invitation.
Thanks. Okay, so I would also like to thank all the participants and wish you a good, productive week. So, and see you again next week.
Thank you. See you. Bye.